The CLO for this lesson is that students will be able to convert in writing between representations using graphs, tables, and situations, as well as the following language. Transition words. Remember, transition words are the words we use to go from one thought to another, things like therefore or but, however, in comparison to, and also because. So those are transition words that we're going to try to use in this lesson, as well as vocabulary words like representation, independent variable, dependent variable, situation, graph, table, coordinate plane, and coordinate pair. Normally, I begin videos with explaining the vocabulary. However, this time around, this is going to wait and we'll start the vocabulary in a minute because I'm going to explain this unit is the start of most of what high school math is about. It hits a lot of competencies. So, in order to graduate, you have to prove you're competent on certain skills in math class. And one of the skills in math class that they want you to be competent on is called going between representations for all function families. So, that's one of the things that they're going to expect you to do. And so in every math class, there's different units about the different function families. So you'll hit a unit about a certain type of function family, and you're going to be expected to go between all the different mathematical representations of them. But in order to do that, you have to understand what a mathematical representation is. So the point of this video is to make sure that you remember what the different mathematical representations are and how they are connected to each other. And then you will learn throughout your 4 years of high school math, different type of function families, and then you're going to be expected to be able to go between all the different representations. So to quickly explain what I mean by function families, there are many types of them. For example, constants. When you graph a constant graph, it makes a straight line like this. And constants show up in our real world all of the time. Anywhere there's a flat line, it's a constant. So on a road, a pencil, or the edge of any wall or any desk, constants show up everywhere. So do linears, because linears, if you look at a linear graph, they're also straight lines, but they're not flat. Constants are flats, but linears are diagonal. And you have diagonal lines everywhere in the real world as well. Any edge that's diagonal instead of flat is a linear. You also have exponentials that look like this. They're kind of curvy and shoot up. Quadratics are curvy on both sides. I put this example here of like, look, bananas are quadratics because they kind of have this U type of shape in their curve. Square roots. If you look in this tree, kind of this edge on the right makes that little square root shape. And so this is what the graph looks like. It's kind of like curvy up on one side. Cubics look like this. Cube roots look like this. Absolute values look like little V's. They show up in like, think about sun rays and how like, if you were to draw a picture of the sun, the rays would look like little V's everywhere. And there's tons more. These are the main 7 we're going to focus on in high school. But there's tons of other function families out there that make different shapes. And we need all these function families in real life because they show up in real life. And so, like, for example, if you think of a roller coaster, they can't make roller coasters if they don't know the equations of all the little parts. And they figure out those equations by using math. And that's how they make them. So a lot of your units in math class are going to be to take each type of family. So like linears is a whole unit in the first year of math. Exponentials is a whole unit in the first year of math. Quadratics is a whole unit in the second year of math. And you're going to learn about the different types of family functions. And you're going to be expected to be able to take each type and know all of their mathematical representations. And not only know them, but how to go between them. So let's talk about what a representation is in general. A representation is a way to express all independent variables with their dependent pair. So in math, representations, they allow us to represent independent and dependent variables. So let's talk about what they are. So an independent variable in math is something that exists alone. It is not affected by anything else. So there's lots of things that are independent in our real life, but the main one is time. Because time just goes by. It exists all alone. Nothing affects times. Like minutes are gonna go by, seconds are gonna go by, days, years, months. Like time is just gonna keep going. Hours are gonna go by. And then as time goes by, things change. And what changes is your dependent variable. So dependent variables change depending on the independent variable. So it is affected by the independent variable. So usually what's affected by our independent variable by time is the amount, how much we have. So examples of this: how many hours you work affect the amount of money you make. Another example might be years that go by affect your height. What else? We might chart your age of a person affects the amount of time spent on technology. So these, the first thing, hours, years, age, those are all independent. They all just exist. Your age just is. The years that go by, the hours that go by just is. But the dependent variable changes based on that. Like the amount of money you make can change, your height can change, the amount of time you spend on technology can change, and it's usually based on the independent variable. So in math, our independent variable is always known as x. So x is the independent variable, and the one that's changing, y, is the dependent variable. So another way to think of the word representation is it's anything with x and y. So in math, there are tons of things that have x and y in it. For example, situations, tables, graphs, and equations. These are our 4 types of representations. The 4 representations in math. So in math, I can always give you a situation. A situation is a real life event that has an independent and dependent variable. To make it mathematical, you need to have both the independent and dependent variable as a part of it. So there are tons of real life situations. Like today I went to the grocery store. That has nothing to do with math until I said after 3 seconds I was this close to the grocery store, and then after 5 seconds I was this close to the grocery store, because then how close I was depends on how much time has gone by. So in order for it to be a mathematical representation, it has to have both the independent and dependent variable. A table is when you chart your independent and dependent variable. So tables usually have your x and y side by side, or in some way, and it's where you're just charting all of the different independent and dependent variables that you have. A graph is where you plot the independent and dependent variable on a coordinate plane to create a picture of the representation. This is a type of representation where we're making a picture by plotting points. And then finally, an equation is a string of numbers and letters that explain what happened to the independent variable to get its dependent pair. So in equations, you plug your independent variable in to the equation to determine what its dependent variable is. So this whole time I keep using the word variable. Hopefully you know that just means something that can change. So the time that goes by can change, the amount you have can change. So variable just means change. And in math, when things can change, we use letters to represent it, which is why the independent variable is x. We call it x. And the dependent variable is y, because we use letters to represent things that could change. So like I said, one of the competencies is for all types of functions, not just linears. However, this unit's about linears. But eventually for all of them, they want you to be able to go between all of the representations. However, the notes today are specifically about taking a situation and then making a table. And then once you have a table, making the graph. A lot of future lessons will teach you how to do the rest of them for linears, but this is where we're going to start. So let's talk about going back and forth between all of them. Here's the situation I have. So here's an example. Situation's telling me that I checked my piggy bank and I realized that I only have $3. So I decided to earn money by doing the dishes. My mom's going to give me $1 every time I do the dishes. Well, to make sure this is a mathematical situation, I need to have an independent variable and a dependent variable. So independent variable is something that exists no matter what, and it's usually about time. So in this case, do you see time anywhere? Well, I don't see the words years, days, months. And then dependent, so let's move on to dependent variable. Well, dependent variable is usually an amount. Do I see amount anywhere? I do. I'd see the amount of money I have. So my dependent variable is the amount of money I have. And what is the amount of money I have based on? Well, it's based on how many times I do the dishes. So my time in this case is how many times I do the dishes. So this is a mathematical situation because I have an independent variable and a dependent variable. Well, if I were to start listing my situations out, let's do points. Remember, points always look like this, where you list the x first, then the y. Well, remember, x is the independent variable and the y is the dependent variable. So in this case, what we're going to list first is how many times I do the dishes. What I'm going to list second is the amount of money I have. So these are the points and how we're going to write them. So for example, I do no dishes. 0 times I do the dishes. How much money do I have? Well, it says in the beginning, I realized that I only have $3. And that was before I did the dishes. So I'd have 3. Then let's say I do the dishes once. Well, if my mom gives me $1 every time and I have 3, once I get my dollar for doing them, I'll be at 4. Then if I do the dishes again, so now I've done them twice, she's going to give me another dollar. So I'll have $5 now. Based on my situation, these are some points I could pull out of it. I could do more, but I'm going to stop. And I can take these points and I can put them in a table. So remember, a table is just a chart that lists our independent and our dependent variable side by side. Remember, independent is always the x, and then dependent's the y. So for this case, my x, my independent variable, is how many dishes I did. So if I did none, I had $3. If I did it once, then I'd be at $4, and if I did it twice, I'd be at $5. So a table is just the independent variable side by side with the dependent variable. It could also, so this is one where the x is on top and the y is on bottom. They can also turn them side by side, where the x goes on the left and the y goes on the right. So in the exact same way, if I did not do any dishes, I'd be at $3. If I did it once, I'd be at $4. And if I did it twice, I'd be at $5. All I'm really doing is taking my points from my situation and putting them into a table. Here, let's zoom out so you can see both styles. A lot of people will just put x and y here. You could put independent and dependent variable. You could even write what they were. Like I could say, instead of x, I could say times I did the dishes. Instead of y, I could say money I have. They mean the same thing. Yeah. Okay, so you can take points from the situation or points from the table and put them into a graph. So a graph is just a different representation of the same information. So remember, our information this time around was this, because if I did 0 dishes, I had $3. If I did them once, and after I got $1, I'd be at 4. And if I did the dishes twice, after I got another $1, I'd be at 5. So these are my points. Remember, points are always written x comma y, where the independent variable goes first and the dependent variable goes second. So this right here is called a coordinate plane. Some people will say, Miss, that's a graph or a blank graph. The name for this is not graph. A coordinate plane is a blank x and y axis. And that's exactly what we have right here. Is this blank x and y axis. Remember, this dark line is what axis? It's the x-axis. And then this up and down line, this dark one here, is which one? This one's the y. So this is called a coordinate plane. It doesn't become a graph until we put points on it. So graphs are the points that are on the coordinate plane. It's not the coordinate plane itself. This is just what we put points onto. For example, think of a painting. When there's a blank painting, right? If you try to type in blank painting, you even try to pop up the word for it, it's called a canvas. So like if you were to look, these are canvases. They're not called paintings yet. They're not called paintings until you put actual paint on them. Then it's a painting. So in math, in the same way, this isn't called a graph yet. If I said, where's the graph? You would have to say there is none. There's nothing there. It's just a blank coordinate plane. However, once we start putting points onto it, then it becomes a graph. Let's just talk about the coordinate plane and what it means. It kind of works like a map, where the x-axis and the y-axis meet in the middle. It's called the origin, but that doesn't really matter. The middle is called the origin, like the original spot, origin, original. And right in the middle, the point is called 0, 0. If I put a point right here on my graph, right where the two axes meet, they call it 0, 0. So the reason why it's called 0, 0 is because the first value is always the x and a point, and x tells you how far left or right to go. And if it's right in the middle, it has not gone left or right. Then y, the second one, tells you about up or down. And right now, it has not gone up or down at all. It's right in the middle. So that's called 0, 0. So from the middle, let's start with x. So x, if the x is a positive x, it's going to tell you to go to the right. Because when we go right, that's the positive direction. So if I go right one tick mark over, they usually label this one 1, positive 1. And then if I go right again, now I've gone over twice. And if I go right again, now I've gone over 3 times. So the right side, all of this over here is all positive. Because remember, it doesn't matter if I'm going up with the y or down with the y. Because for the x's, it doesn't matter if it's over here, it's positive. So any point over here has a positive x. Same with down here. Any point over here will also have a positive x. Because do you see how there's like 4 little boxes? Here's one little box, then beneath it's another one, and then over here's another one, and there's another one. But for both of these two, when I go to the right, it's a positive x. Versus for negative x's, that would mean I'm going towards the left. Because from my middle, if I go left 1, it's like I'm going backwards 1, or negative 1. And then if I go backwards again, now I've gone backwards twice. And if I go backwards again, now I've gone backwards 3 times. And so that's negative 3. And so if I'm going this way on the x-axis, then it's a negative x. So for any point you have, the first part of it tells you if you're going left or right. The second part tells you about the y, and if the y's are positive, that means you're going up. So for y, if I go up 1, that's positive 1. If I go up 2, that's positive 2. So if I'm going up, the y is positive. And then this side is also me going up from that middle. So if they both end up being positive numbers, then you'll always end up in this box up here. Which is why some graphs, there's a lot of graphs in this world that look just like this, where they put x here and y here. And then they call this 0, 0, and then your whole graph's over here. It's not like the other parts aren't secretly there, like this part and this part with the other 4 squares. It's just that because so many things in real life have both your x and y being positive, they're just zooming into like this part of the graph. So it's like they're just taking this little square out only and only focusing on this part of the graph because they're like the rest of it has negatives, and a lot of real world situations don't have negatives. So all this graph is like just taking out the positive box and only graphing in this part. So then to finish it out, if my y's are negative, that's how you know to go down. And so like if I'm down here, that's at negative 1, another one's at negative 2, another one's at negative 3, for example. So anything that goes down has a negative y. So this is the gist of a coordinate plane. So if I were to give you any point in the world to graph, the important part is you always have to do both instructions before graphing. For example, if I wanted to graph 1, 4, this 1 is a positive 1, which means it would go right 1. So I'd have to go right 1, but then I do not put a dot yet. I have to do the other one, the up 4 one. I have to go up 4, then I can put my dots. Because you have to do both things before you place your dots. Why don't I show you? Let's graph all the points from our situation. But to do it, I'm going to use Desmos. So in Desmos, I can add a table. So if you remember, 1 point was that 0, 3. So if you look where my little green dot showed up on my coordinate plane, this is where my graph is right now. It's just 1 point, 0, 3. And 0 means it does not go left or right, but it did go up 3. One thing to notice is that this tick mark says 2, and this one says 4, instead of it saying 1 and then 2. And then because they decided to count by 2s on this graph. But let's say I zoomed in a little. Now it's counting by 1s. If you see, the first tick mark's 1, the next one's 2, the next one's 3, and that's where that dot is. So you can always change your scale here. Let's look at it like this. You can always change your scale to make each big tick mark mean what you want. But that means that if you zoom out, then you have to be good with fractions, because where is 3 between 2 and 4? Well, it's halfway in the middle. And if I zoom out some more, now where's 3 between 0 and now the first tick mark's at 5? Well, you would have to know that 3 is a little bit above half when it comes to 5. And then if I zoom out even more, now the tick marks are going by 10s, and you have to see, like, look how low 3 is on a scale from 0 to 10. So you can scale your graph and make your tick marks go by whatever you want. But if you say this one's 10, the next one has to be 20. Like, it has to be the same amount for each tick mark. And then when you place your dots, you just have to guess really well about where they should maybe go. So let's go back into the 1 scale. So then my next point was, if I did it 1 time, I had $4 altogether. So you see this point showed up right here? It's because we went right 1 and then up 4, and then that's where that dot goes, that 1, 4 point. Next was that after 2 times of doing the dishes, I had $5. And now here's that third dot right here. And so if I'm just graphing these 3 points, this is the graph of the 3 points. Now, a lot of the times people will then connect their dots. And sometimes you can do that and sometimes you can't, but I'm going to explain that in a second. Let me just come back to the notes real fast. So we plotted the points on Desmos, and so that's one way to represent situations is by a graph. The last way they expect you to be able to represent a situation is with an equation. And it's really hard to figure out equations of things. Like, if they don't start you with the equation's usually the easiest one to start with. Because if they start you with a table or a graph or a situation, figuring out the equation's kind of hard. And that's what a lot of the math classes are about. Like, a lot of the units will teach you how to figure out different types of equations. But until then, what the important part of the equation is that what it is it's something you can use. Something you can use to plug in any x value and figure out the y value. It represents what happens to the independent variable mathematically. So in this case, my independent variable, how many times I do the dishes, I get $1 for that. So like if I did it 5 times, 1 times 5, that would be $5. But then I still have to add the $3 that I already had to figure out how much I have in total. Well, x represents how many times we did the dishes, and 1x is the same thing as just x. So this equation represents our whole situation right now. And you'll learn how to do this quicker later on, but let me show you the use of the equation. If I have an equation that says x plus 3, I don't know what that x is. I can plug in any x I want. Well, let's say I start doing the dishes and I'm like, I don't want to do them all. I only want to do half of them. So I type in 0.5 for half. Well, then if I only do half of the dishes, My mom's only going to give me 50 cents. So I only have $3.50. And so I put that point in my table now. And look how it's kind of close. It's in between the 3 and the 4. So let's do another decimal. Let's say my mom says I can do decimals of the dishes and earn, let's say I can open things by the penny. So let's say I only do a penny's worth of dishes. So then I have $3 and a penny. So I only do 0.01 dishes and I have $3 and a penny. Where is even that point? It almost looks like it's by that one. If I zoom in really close, oh, now you can see they're separate. But when I'm into like the decimals for tick marks. But when I zoom out, you see how close they look together? So much so that when I zoom out all the way, they almost look side by side. What happens if I do O2? Well, that's 302. Then I have $3.02. Now 3 would be $3.03. So if I super zoom in, you can see all those points right there. They're all separate points. But when I zoom out, they look like they're all almost 1 point. Let's do 10 cents worth. So then I get $3. If I do 10 cents worth of dishes, then I would have $3.10. Then maybe 15 cents worth. So $3. If I do 15 cents worth of dishes, I would have $3.15. Then maybe 20 cents, which is $3.20. And then 25 cents would be $3.25. So this is a simple equation because it's just the dishes amount plus the amount of money I had. It's just X plus 3. So as you can see, the more and more decimals I do, the more and more when I zoom out, it starts to look like a line. You see how it's starting to connect itself? So when you are connecting your dots, it's not like there's just 2 points or 3, like this one, and this one. There are millions of points because like I zoom in, right? And now they don't look like they're side by side, but I could even add little decimal points in between all of these to make it eventually connect all the way through. So what an equation does, when instead of plugging in things to equations, if I write X, and it's going to turn up red. You see how this is red? The equation is going to turn up red here. Plus 3. You see this line that's connecting all of our points that we had? It's not like we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points on our graph. We have billions and millions and trillions of points on our graph. And they're all just decimals. Like this one here, 0.743 or 0.746 and $3, 0.746. Like all a line is millions upon millions of points super, super, super close together that make a line. And it would be ridiculous for me to tell you to plug in every decimal in the world and graph it. It would take your whole life. Like it's not something that I want you or expect you to do to make the picture. Instead, I'm going to teach you fast ways to graph things. Like on these types, if I didn't have any of these other points at all, none of the other points on this graph, minus those first 3, I could have just connected them, and then I would have got my graph. The important thing here is that you know that it's not like there's only 3 points on this graph. There are millions upon billions of points. That's a point, that's a point. All of these are little points. And that's why it just looks like a line. All right, so those are the 4 mathematical representations. They all represent the same things. The situation just tells you what it's about. And that's how you represent it, by understanding what's going on, like in real life. The table just represents it in a way that you can see your points very side by side like. and it represents it in a little chart. Then the graph ends up representing it like a picture. And the equation represents it in a way that allows you to figure out any x you plug in, what's the exact y. Because with tables, for example, if you look at this and I'm like, all right, what if I did the dishes 20 times? You would have to keep going, to figure it out. If it was in a graph and I said 20 times, you would have to go over to where the x is 20 and go up and try to estimate, like, where is that? I'm not quite sure. But I know for a fact when I put 20 into my x, the answer is 23. Because that's what the equation does, is it lets you figure out precise values and exact amounts versus a graph that will let you see the trend of data all at once. Like, they all have their different values. We need them for different reasons, which is why they expect you to go back and forth between all of them, which you will learn how to do in mini units. So to can summarize exactly what we've learned so far, in blue, today, we learned how to take a situation and figure out its independent and dependent variables so that we can make a table. And then we could take a table and graph it. I also talked about how if they started you with an equation, you can just plug in any x you want so that you could also make the table and graph it. And finally, the last one I want to mention is going from a graph to a table is also really easy. Like, let's say I have this graph and I needed to make a table out of it. Well, on any single point that exists, and there's millions of them on this line, I can pick any one of them. Like, let's say it's easiest to pick where they cross grid lines perfectly. For example, if I wanted to pick this point right here, where I'm putting my red line, it would be a bad point because if I try to find the x value, it's going to be a decimal that I'd have to guess. And if I go over to the y value, that would be a decimal that I'm trying to guess. But if I find a perfect cross, like right here, this point on that blue line crosses at a very clear x and y value. So if I go down to my x, it's down here, right here at -2. And my y for this point is over at 3. So to put that point into the table, when my x is -2, my y was 3. And I can do it for another point that crosses perfectly. Like right here. Here's somewhere the blue line crosses the grid marks perfectly. So the x for that point, it's on the x-axis. So it went from the middle, it went left 9. So it's at -9 for x. The y is how far up or down that point went. And from the middle, it does not go up or down. Because it's on the x-axis, remember, that means it's an x-intercept. And that means it's not going up or down. So the y is 0. Another point, so it's best to read graphs from left to right. So if I start in the left and start moving, this is another good cross. This is another good cross. That one would be a decimal. That one's definitely a decimal. Decimals. I think that's a decimal. I'm not sure it's crossing perfectly. This one crosses perfectly. Right here. Tons of decimals. This one goes through the grid marks perfectly. And this one goes through the grid marks perfectly. So because I have so many points that go through the grid marks perfectly, I can use these ones to make my table. So I did, and normally tables start with the smallest x first, so left to right. So it should do -9 and then 0 first. Then this one is at -8 for the x value, because from the middle it went backwards 8, but then it goes down 1. You see if I go over to that line, it's at -1. So I had -8 and -1. My next one, this point, the x is at -7, and the y is where? What's the y for this point? If you look towards the right, you see it went down 2. So from the middle, I had to go left 7, so -7, then down 2. So x would be -7, and y would be -2. Now this is more than enough points to be a table, but just for practice, let's put the other points on there. For this point right here, what's the x? If you look down, it's at -3. And what's the y for this point? It's at +2. This was the point we already did, the first one, but what is the x for it? It's at -2, and the y is +3. Remember, this point was just the decimal one that we shouldn't do, but then this one, what's the x for this one? X is 5, and what's the y? The y is 3. And finally, for this point right here, what's the x? Well, after 9 would be 10. And the y is what? We'd be going down 2, so -2. So now all the points that I can tell easily on this graph, I put into a table. And that's just how you would go from the graph to the table.